At this point, all of you should be aware that all matter is made out of chemicals, and all chemicals are made out of atoms, and every atom belongs to one type of element. And if you watched the previous video, you know that the differences between two atoms of separate elements is going to come down to the number of protons they have in their nucleus, which is accounted for by the atomic number. The more protons an atom has, typically the more electrons it will have too, and the way that those electrons fit into shells around the outside of that atom account for all of its chemical properties. Specifically, it is the number of valence electrons that determine how a given element will behave. For example, the number of valence electrons will determine the bonding behavior of certain elements. Here we have a few different atoms. These white ping pong ball looking atoms are hydrogen atoms, and these red ones are oxygen atoms. And you can see they're paired up. When multiple atoms are paired up like this, we say that they are bonded together, and there are three different kinds of chemical bonds that we are going to discuss in this class. When atoms are held together by a chemical bond, they form what is called a molecule. And when you have two molecules that come together and they rearrange their chemical bonds, we call that a chemical reaction. It's kind of like a square dance, like a do-si-do, where they're constantly changing partners around with each other. Atoms are constantly rearranging themselves. So here we have two molecules on the left. These are hydrogen gas and oxygen gas. We have two molecules of H2 and one molecule of O2. And then if we react them together, we get that chemical do-si-do, and then we end up with two molecules of H2O. Now notice that we didn't add or subtract any atoms from this chemical equation. We started with two oxygen atoms, and we ended with two oxygen atoms. That's the red ones. We started with four hydrogen atoms. 2 times 2 is 4. And then we end with 4 hydrogen atoms. You cannot create or destroy matter in a chemical reaction. You can only rearrange how they are connected with each other. So if I wanted to make water, this is a plausible way that I could go about doing it. I could get some hydrogen gas, I could get oxygen gas, and I can mix them together in a 2-to-1 ratio, and then add a little spark to get an explosion, and one of the byproducts of that explosion, in addition to heat and release of energy and light, would be water vapor. I would get water vapor out of that. Now you might say, like, well, why do you need to use H2 gas and O2 gas? If you want to make H2O, why don't you get just 2 hydrogen atoms and 1 oxygen atom and just add them together like that? Why do you need to go to these other kinds of molecules that are already in their own particular arrangement? And the reality is that atoms never really show up just by themselves. It's very rare that you would find an element, an atom, just of a single element, floating around completely unattached to anything else. Atoms like to make bonds, and I'll explain why in a little bit. But in the real world, you are always going to have reactants, the chemicals that you are putting together, and then products, the chemicals that are the consequence of that chemical reaction that you just pushed forward. Now, what would cause two molecules to react with each other? Why aren't they just satisfied with the elemental partners that they currently have? Why do these atoms need to switch around? Well, in order to react, two molecules are going to need to collide with each other. Now, where would I get a situation where two molecules are going to collide? It's actually more common than you might suppose, because molecules are constantly in motion. And if we have molecules that are in a gas, that's a lot of motion. Those atoms, those molecules, they're going to be moving around constantly in every which random direction, and periodically they're going to smash into each other. When they collide like that, you can get a chemical reaction. They can start switching partners around. And we can call this idea collision theory. In order for two molecules to react with one another, they essentially have to smack into each other like two cars in a head-on collision. You can imagine if two cars smash into each other, you're gonna, if you separate the two, you'll have some headlight from one car on the other car, and you'll have a little bit of paint transfer from car B over to car A. They're going to exchange a little bit, right? And that's the same with these molecules. Now, anything that would increase the number of collisions that would make these molecules more likely to smack into each other is also going to increase the rate of a chemical reaction. So what kind of things could we do to make more and more collisions happen? Well, we could increase the temperature, for one. Temperature is a measurement of the overall kinetic motion of molecules in any substance. And if we increase, so let's start with a solid. If we increase the temperature from a solid, then the molecules go from being not very mobile at all to suddenly vibrating in place. And eventually they vibrate enough that they kind of shimmy loose of each other, and you melt that solid and you get a liquid. If you increase the temperature even more, then they start shimmying so much that they can actually escape from one another, and you get yourself a gas. And the more freely molecules are able to move around, the more impact they can have when they do in fact smash into each other. So increasing the temperature is one way that you could increase the rate of collisions. Another way is to increase the pressure or to use higher concentrations of the chemicals, both of which would have the overall effect of decreasing the average distance between any two molecules, and that would mean it's more likely for them to collide. Imagine we have bumper cars, right? And if I just keep adding more and more and more bumper cars, eventually a safety inspector is going to tell me to stop because it's entirely too dangerous. Too many collisions per second going on. But in chemistry, that's what we want. Maximum collisions, because that means maximum reactions. We could also mix up our chemicals in what's called a solvent. We can take a liquid and put two other materials that we want to react together mixed up inside of that liquid. And you've probably seen in any kind of movie where there's a scientist, they're always mixing stuff in beakers. Well, that's essentially what they're doing most of the time. They're taking materials that they want to react together and they're putting them in this medium that would allow those chemicals to react. And the reason I bring this up right now is because in a little bit we're going to talk about some of the special properties of water, and one of them is that water is a remarkably good solvent. It is a great medium for chemical reactions, and that's one of the reasons why it's important that your body is mostly made out of water, because there is a lot of chemistry required to keep you alive. So just a moment ago, we had an example of two hydrogen atoms that were bonded together and two oxygen atoms that were bonded together, and they are called molecules, right? But if you have a molecule that is made up of more than one kind of element, like water that we also had in that previous example, that's not just a molecule, it's a compound. So a compound has more than one kind of element in its structure. Here we have two different kinds of compounds. One is water, which we just saw, H2O, and then the other is NaCl, table salt, sodium chloride. And you'll notice that they're a little bit different from each other. Each water molecule has exactly two hydrogens and one oxygen. Compounds are substances that contain two or more elements in a fixed ratio. So 2 to 1 is the fixed ratio for water. However, a crystal of sodium chloride could have really any number of sodiums or any number of chlorine in it, but the two numbers will be roughly equal. There will be roughly a 1-to-1 ratio between the amount of sodium and the amount of chlorine. So if you have 500 sodiums, you'll also have 500 chlorines. And it might not surprise you to learn that since the rules of the ratios of the elements in these compounds is so different, that these two kinds of materials have very different chemical bonds from one another. So here we're going to take a look at those two different types of chemical bonds. One of them that you find in water and the other one that you find in sodium chloride. All chemical bonds form because there's a change in the condition of the valence electrons of the atoms that are involved. In the case of water, it forms via covalent bonds. In a covalent bond, the atoms that are involved are sharing one or more pairs of valence electrons. Since those valence electrons are in the valence shell of more than one atom at the same time, they are covalent. They're in two valence shells simultaneously, and we call these covalent bonds. So here I have an animation of two hydrogen atoms that are going to collide into each other, and when they collide, they form a covalent bond, which is an overlapping of their two valence shells, and you can see that the electrons are now able to go around both of them simultaneously. Because these electrons no longer exclusively belong to one atom or the other, the two nuclei of the hydrogen atoms are held together in position. They become a single solid object. Now, why are the atoms sharing their electrons at all, though? Like, we understand, yeah, they just smacked into each other, but why, when they did that, did they decide to share their electrons? Well, it comes down to something we were talking about last time, which is the number of electrons that can fit into the outermost shell and how many valence electrons each type of atom has. the number of covalent bonds that any given element, any given atom can form is going to be equal to the number of additional electrons it needs to fill its outermost shell. So I wasn't teaching you about the structure of electron shells for no reason. You really do need to know that 2 electrons can fit into the first shell, 8 electrons into the second shell, and 8 electrons into the third shell. Every atom that we talk about in this class that's larger than hydrogen is going to want 8 electrons in its outermost shell, and it can get those 8 electrons by either sharing them, giving them away, or stealing them. So we'll see some other examples where it's a little bit more extreme, but covalent bonds are all about sharing. Now, if you take a look at hydrogen here, you can see that it's got 1 electron in its outermost shell, but that first shell can hold 2, right? So it can make just one covalent bond. Hydrogen always makes 1 bond. Carbon, which I previously said is one of the most important elements in biology, here is the big reason why. Know that if you learn nothing else from the chemistry section, learn this part. 4 bonds to carbon. Carbon can make 4 covalent bonds because carbon is atomic number 6. It has 6 protons, therefore it attracts 6 electrons around it, so a neutral carbon atom has 6 electrons. 2 of the electrons go into the first shell, then it's full, so we have to move to the next shell out. And then you have 4 left over to go into that second shell, but the second shell can hold 8, which means that carbon has 4 slots available for bonding. Nitrogen is right next to carbon on the periodic table. Carbon is number 6, nitrogen's number 7. So since it has 1 more proton, it also has 1 more electron, which means it only has 3 slots left over for bonding. Oxygen is right next to nitrogen in the same way, and oxygen can make 2 covalent bonds. So let's try this. I'm going to take carbon, nitrogen, and oxygen, and for each of those 3 elements, I'm going to fill out its maximum number of bonds using hydrogen. Hydrogen can make only 1 bond, so every hydrogen will just be bound to that central atom, and we'll see what kind of chemical compounds we get out of this. With a carbon atom, since we can make 4 bonds, we get a chemical compound with the molecular formula of CH4, 1 carbon, 4 hydrogens. And here's what it would look like. It looks kind of like a little pyramid. This is methane. Methane is a natural gas. It's what we call a hydrocarbon. It's a compound that's just made out of hydrogen and carbon, logical enough. And hydrocarbons contain a lot of energy. We burn them for fuel. So you find a lot of hydrocarbons in, for example, gasoline. Similar types of compounds are found in a lot of the food that we eat, and we'll talk about that a little bit later on. For each of the bonds that you see here, every hydrogen is donating 1 of its electrons. It's putting 1 electron up for sharing, and each carbon is also putting 1 electron up for sharing. So both of these elements are happy with the arrangement. Because electrons are so fast and because their exact position can't really be nailed down, even though these atoms are sharing electrons, both carbon and hydrogen get to treat the electrons like they have full custody of them, like these are their own electrons. And if you look at the molecule as a whole, you might notice that the total number of protons and the total number of electrons hasn't changed. So this is still going to be a molecule with a neutral charge, which is another thing that atoms like, is to be neutral. So this is a really happy arrangement for carbon and hydrogen. Because carbon already has 4 electrons and it's getting an additional 4 from hydrogen, it gets to pretend that it has 8 outer shell electrons. Every hydrogen is getting 1 extra from carbon, so it gets to pretend that it has 2 outer shell electrons, which would fill up the first shell, so it's happy as well. I mentioned in a previous video that elements like to be neutral. Another thing that they like is to have a filled outermost shell of electrons. That's their most stable configuration, and everything in nature wants to be stable. Now, if I do the same thing with nitrogen, you might remember that nitrogen can only make 3 bonds because it has only 3 spaces left over in its valence shell. I'm going to get NH3. NH3 is ammonia, which is another kind of chemical you're probably familiar with. It's a really good solvent in certain situations. Now, if we use the same idea with oxygen, what we're actually doing is the same chemical reaction that I showed you at the very beginning of the video. You might remember we took 2 molecules of H2 and 1 molecule of O2 and reacted them together. Now, oxygen can form 2 bonds per atom, So how does this O2 work, right? If you just have one bond between these two oxygens, why are they happy and content to be there with themselves? Well, oxygen actually forms a double bond with itself. You can actually share more than one pair of outer shell electrons, and every time you share an additional pair, you can get a single bond, a double bond, a triple bond. Two nitrogen atoms actually will have a triple bond with each other. Double bonds are stronger than single covalent bonds. Triple covalent bonds are stronger than double covalent bonds. If we were writing out a chemical formula, we would signify that there's a double bond with 2 dash lines, and we would signify a triple bond with 3 dash lines, same idea. Now, if we do this reaction, we do this chemical do-si-do, and we combine oxygen and hydrogen together, again, we get water. One thing to note about water is that the covalent bond is a little bit different from the one we explored with the methane molecule. They're still sharing their electrons. Hydrogen and oxygen are sharing their electrons, but they're not sharing them evenly. The oxygen is actually very greedy for electrons. This is something that you'll hear me say a couple of times throughout the semester. Oxygen is greedy for electrons. It pulls on the electrons very, very strongly. So the electrons spend more time around the oxygen than they do by the hydrogens. And if the negative charge is spending all of its time down with the oxygen, you're going to have a little bit of negative charge on the oxygen itself. We call this a polar bond. The hydrogens are positive and the oxygen is a little bit negative. Not a full-blown positive or negative, but just a slight imbalance. And polar bonds have interesting consequences associated with them, which we'll attend to in a later video. But for right now, it's enough to know that some covalent bonds have equal sharing. We call those non-polar covalent bonds. That's like methane. And some covalent bonds have unequal sharing. We call those polar covalent bonds. And that's what you would find in water, as well as a few other materials. Now, what would happen if there was an atom that was even greedier for electrons than oxygen is? It's not just going to share them unevenly, it's actually willing to just steal electrons altogether. In that situation, we would get what's called an ionic bond. Let me show you how this works. So here we have a sodium atom and a chlorine atom. Now, they are neutral right now, and if you go ahead and check your periodic table, you'll find that sodium is atomic number 11, and you can count up all these electrons and see that there's 11 electrons divvied up between its 3 shells. Now, chlorine, on the other hand, chlorine is atomic number 17, so it's got 17 protons and it's got 17 electrons. 2 electrons go into the first shell, 8 go into the second shell, and then there are 7 left over for this third shell. So you can see that it only has 1 slot open on its outermost shell, on its valence shell. So that's the situation at the start. We have 2 neutral atoms. Sodium has 1 electron in its outermost shell. Chlorine has 7, and in order to meet its octet, it's going to need 1. Now, sodium could fill up its octet by creating covalent bonds with 7 other atoms, but in reality it can't. There's just not enough space for enough atoms to get around it to do that, and ultimately it just takes a lot of work to do that kind of thing. But sodium has a much easier option available to it. Instead of trying to make as many bonds as possible, what if it just got rid of this valence electron, the 1 electron that it has in its third shell? If it gets rid of it, well, then this second shell becomes its outermost shell, and then it has a filled outermost shell of electrons. Now, that might seem like a little bit of a cheat, but this is a valid way for an atom to get a filled outermost shell of electrons. Now, chlorine's in the opposite situation, right? It just needs that 1. So if sodium's going to give away that electron, then chlorine's going to be there to scoop up that electron. Or if you like, you can imagine that chlorine is stealing the electron from sodium. Either way, both of them are happy. Now, if you are subtracting a negative charge from sodium, subtract a negative in math, what do you get? A positive. So sodium becomes a positively charged atom. Chlorine gains a negative, so it becomes a negatively charged atom. We call charged atoms ions. A positive ion, like this sodium here, is a cation. A negative ion is called an anion. Kind of like if you've ever tried to jump your car battery and you have the anode and the cathode, right, the 2 ends. Same idea here. So the positive is the cation and the negative is the anion. Now wait just a minute, I hear you say. You said that atoms don't like to have a charge on them, that they always want to be neutral and have the same number of protons and electrons. So what's with this exchange nonsense here? What's with these ions? They do want to be neutral wherever possible, but they also want to have a filled outermost shell of electrons, and when push comes to shove, they would rather have the filled outermost shell of electrons than they would like to be neutral. So you get these atoms that form ions when you mix them together. Sodium forms a positive ion, and chlorine forms a negative ion. However, remember from our discussion of charges that positive attracts negative. So now that we have two oppositely charged ions, what's going to happen? They're going to magnetically attract together, and they're going to form what we call an ionic bond. So an ionic bond occurs when there's not a sharing of electrons, when there's a complete and total transfer of an electron from one atom to another atom, creating two oppositely charged ions. And what's amazing about chemical reactions, this is true of both the formation of covalent bonds and ionic bonds, is that the materials that you start with, whatever the properties of the materials you start with are, they're not necessarily going to be the same as those properties of the new chemical compound that you are creating. So, for example, sodium is a metal. You might not think about it because we always think about sodium in the context of sodium chloride, right? It's this kind of mineral salt that we put on food. But if you have pure sodium, it's actually a metal. It's kind of gray, and it's really, really soft too. You can cut it with a kitchen knife. Sodium is an extremely reactive metal as well. If you expose it to, say, water, it will react so energetically that you'll get a massive explosion. It has to be kept in very careful conditions when we store it in chemistry labs. So sodium is this explosive metal. And then you have chlorine. Chlorine is the stuff that we put into swimming pools in order to kill bacteria. It's the stuff that they used in chemical warfare in order to clear out foxholes. Right? So this is a really toxic, nasty, poisonous gas. So you take this explosive metal and this poisonous gas, and you react them together, and you get an edible rock. That's insane to me. Like, that the properties of the compound have almost nothing in common with the properties of the individual elements that make them up. And this is what chemistry is all about. If you change the bonding, if you change the position of electrons, if you change the relationship of these elements to each other, you can create fundamentally new kinds of material from those earlier starting components. So where are we so far? We've talked about chemical reactions, we've talked about elements, we've talked about atoms, protons, neutrons, all this kind of stuff. And you know the difference between covalent bonds and ionic bonds. Covalent bonds means two atoms are sharing their outer pair electrons, their outer shell electrons. An ionic bond means that there's been a complete and total exchange of electrons from one species to another, from one atom to another. Another kind of bond that we're going to look at is called a hydrogen bond, and this is sort of a byproduct of the polar covalent bonds that we talked about a moment ago. But since hydrogen bonds are so important specifically to the functioning of water molecules, I'm going to talk about them in the next video, which is all about the properties of water.